Alright, so I figured since I'm already doing these, I might as well do the other one. So here we go. Amir Hodzik's Physics 203, 2015, the dome problem. This is our other problem that was told to us for the final, and we'll see how this goes. So, draw a free body diagram, and what we have here is we have this big ice dome, right? And the reason why we say it's ice is because it's frictionless. If he introduces friction to this, God rest your soul, because we are all doomed. You got 2 points that really matter in this problem. So to start off, you have this object right here, and it is traveling down the side of the dome, and it's gaining velocity both in the y direction, negative y direction, and in the x direction. We're going to have them going this way, but it's arbitrary. We're going to call this positive x. And so as it does that, at a certain point, it's going to stop touching the dome, right? It's just going to fall off the side of the dome. And that's the point we're trying to find. So we're going to draw a guess of where that point is, right? And we're going to call this the final point of the problem. So the next step is we're going to do free body diagrams for these. Right here, we have, of course, mg down. Going up at the equal and opposite amount is force normal. Now over here, it's a little different. We're going to break this down into components just like you've done all semester. We have mg down, and normal force is perpendicular to the body in which it's on, which is force normal. And then you've got 2 components coming off of this. You have mg cosine theta, another component coming down parallel with, and that there is mg sine theta. All right, we're going to need to know those, so pay close attention to that. So now what we can do is we can deduce from here our forces in either direction, which means that in the y direction, our force is equal to, notice that n is positive, force normal is going up, while these are going down. So normal force minus mg cosine theta, because it's not flying away, so normal force is heavier, or I guess there's more force applied. Yeah, that. And then in the x direction, we know that x is simply equal to mg sine theta. That's the only force in that direction. If there happened to be a friction, then you would be subtracting the frictional force here. So keep that in mind as you do the problem. Now this here is equal to ma, but in the y direction, the acceleration can then be related to centripetal acceleration, which we use v squared over r for that acceleration. So we're going to then relate this to mv squared over r. So that equals, then over here we simply have ma. Alright, so from here, we have an initial and a final. So now we can use conservation of energy. So we're going to come over here, we're going to say energy initial is equal to energy final. Now we know that there are 2 types of energies involved right here. There's kinetic and there's potential. So we'll write them as such for here. So we're going to have 1/2 mv initial squared plus then potential mg h, we're just going to call it h for now, is equal to 1/2 mv final squared plus mgh final. So we're going to define a couple of variables really quick. We're going to say that this distance right here is r. That is the radius, simply enough. And then this distance from here to there, this is our new h. So coming back over to here, we can replace this h right here with an r. Right, so that's r, that's the h initial, here's h final, it's lower. Energy has been expended, turned into kinetic as it's moving this direction now. So, right away, we can simply kill the masses. If he gives you a mass, forget about it, because it doesn't matter. And then we'll simplify further, knowing that velocity initial is 0 in this case, because it's not moving, right? So, that goes to 0. So that 0 multiplied by 1 over 2, 1/2 of 0 is still 0. So this whole thing is 0 right here. So we're left on this side, which is GR. And the other side, we're going to, I guess we'll rewrite this. GR is equal to 1 over 2 V final squared plus GH final, or just GH. We're just going to call this H. All right, cool. So now we have V final squared, and this over here just happens to be a V final. So let's take this and solve for our V final squared. So we're going to come over here, and we know that n minus mg cosine theta is equal to negative mv squared over r. This v squared over r is going to be negative because it is. Just look at the drawing, and I guess we'll label our axes right now. This is the positive y-axis. This is the positive x-axis. Yes, I know it's backward, but we're going to stick to it because I drew the diagram here and not over there. So at this point, we're going to take a limit. We're going to take a limit as n approaches 0. This is because once this stops touching it, there will be no normal force. So as n approaches 0, this becomes 0, so it's just equal to mg cosine theta is equal to negative mv squared over r. The negative m's cancel, and we have g cosine theta is equal to v squared over r, or, simple algebra later, rg cosine theta is equal to v final squared. Alright, so that's what you got once you do this little proof right here. Coming back over here, we can plug that into this right here. So we have gr is equal to 1 over 2, and then we're going to take this right here and we're going to go rg cosine theta plus gh. Okay, so now to make things a little bit easier, we can multiply everything by 2 just to get rid of some simple variables. So now we don't have fractions that we have to deal with. So 2gr is equal to rg cosine theta plus gh. Okay, so at this point, you're nearing the end of the problem, but now we need to figure out a way to relate r to h so we can cancel a few things. We can already cancel g. G can go away. Gravity does not matter if it takes place on a different planet. It doesn't matter. So now we're going to come back, we're going to make another proof, and we'll do that one over here. So, to relate r and g, we're going to come back here and make a triangle, right? The radius does not change, the radius of the circle does not change. So we're going to have a triangle from here to here, from there down, and that across. So, we can relate this by saying that this triangle that we created here of r and h then has a theta, correct? Well, we're going to use cosine here because 90 minus theta is sine, because h over r is equal to sine theta because it's opposite over adjacent. So 90 minus theta then creates cosine. So this becomes r over, so h over r is equal to cosine theta, right? So h is equal to r cosine theta. Amazing, we can plug that in over here. Simplify out a little bit more. 2r is equal to r cosine theta oh, oops, that's also multiplied by 2. Don't forget that. Plus 2r cosine theta. All right, well, we have some like terms right here that we can combine, but before we even do that, we can just cancel the r's. They can go away. So now we have cosine theta plus 2 cosine theta is equal to 2, so we have 2 is equal to 3 cosine theta. This is the same angle, same cosine, so you can equate these. And then, so 2 over 3 is equal to cosine theta. Now, what does this really mean? What's the significance of this? Well, if you come back to this right here and plug this back into here, we know for a fact now that once this is plugged in, h is equal to r2 over 3. Or the height is 2/3 of the original radius of h. And that's it. Now you know the height in which they don't touch anymore. Text me if you have any questions or comment. Subscribe. I don't know. Don't peruse my old stuff. I'm always a weird child.